Welcome to Math 31. This is a lesson covering some of the basic review parts of for Math 31, for the trig unit. It's going to be looking at a lot of the Math 30 pure things fairly quickly, but material that you've all seen before and that you need when you go through the calculus-based trigonometry. So to start, just a reminder about radian measure. In 30 pure, you tend to work with rads a lot, but you also have degrees. And in this course, and in fact for most calculus, you work pretty much exclusively in radian measure. So you need to be good at it. You need to be fast at it. And ideally, you don't spend a lot of time converting from degrees to rads or vice versa. You start in rads and you stay in rads. So a quick reminder that that it is an alternate form of angle measurement. And it's all based on this concept where you have an angle, an interior angle. You have a radius of that circle, and then you have an arc length that is subtended by the angle theta. And the relationship always works like this, that the angle measurement in rads, not in degrees, is based on the measure of that arc length subtended or standing on the angle theta divided by r, the radius itself. And it's useful because it is totally self-contained. It's not imposing an arbitrary system like degrees on it. It's just dealing with the circle. Once you get used to it, very easy to work with. You're dealing normally with exact values. So to convert, I'm not going to spend a lot of time. In fact, I'm going to spend no time on how this formula was developed and how the relationship between degrees and rads came to be. But here's how you will actually convert. If you're going from rads to degrees, you take the measure you have in rads and you multiply by 180 degrees over pi. And then in a similar way, if you're going from degrees to rads, you take the measurement in degrees and then you multiply by pi over 180, and that will convert your answer into radian measure. You may recognize this method as dimensional analysis used in sciences, where you're introducing, in this case, degrees, and you're canceling out pi, which is going to be in the radian measure. And the same thing is true with the other form, with degrees to rads, is that you introduce pi and you cancel out the degree symbol. So let's just do a few of these to get comfortable and then move on to other topics. So we want to convert into an alternate form, either rads or degrees. The 240 degrees is one that some of you might already remember, or you will not have to convert too often because you do have it memorized. It's a special angle, as we call it. But to convert to rads, you multiply by pi over 180. Now the way I do this, the way most people do it, is reduce the fraction, 240 over 180, and you keep it in that form. Of course, in your calculator, it's easy to do because you take the 240, you divide by 180, and then you press math, and then it'll do the conversion for you. You don't even have to press equal. So 240 divided by 180, math, fraction, and there you go. And that will then be equal to 4 over 3 pi. And that's the way you want to keep it as an exact value, because pi is, of course, is an irrational number. Next one, negative 3 pi over 8. We do the same thing. We multiply, except in reverse. We multiply by 180 degrees over pi. You want to introduce the degree symbol and cancel out the pi. So the pi will go away on you, and it really is just a matter of multiplying 3 times 180 divided by 8, and that will give you 67.5 degrees. Keep going for number 3. This is a different one in that it's already a decimalized version, and typically with these ones they'll say round to a nearest decimal value, and I didn't in this case, but I meant it. So you take the 3.4 rads, the irrational value pi has been multiplied in. So what we do is exactly the same thing. We take that 3.4 rads and we multiply by 180 degrees to reduce degrees, and then pi. And you actually multiply and divide it in. So 3.4 times 180 divided by pi on your calculator, of course, so you're decimalizing it. 3.4 times 180 divided by pi, and I'm getting 194.8 degrees. And then finally, number 4, we multiply by pi over 180. By the way, the 67.5 should have been negative 67.5, just like this is going to be a negative value. So nothing really new happening here. 255 divided by 180, math fraction, and you'll get 17 over 12. So this is negative 17 over 12 pi. So you need to be good at that. Now the next batch of questions is going to be based on special angles, which are also very important. So these are exact value measures for certain angles, the 30s, the 45s, the 60 degrees, and then of course the radian equivalents. So quickly go through these and how they're developed. In a 30 pure course, of course, you start with a 2, 2, 2 triangle, bisect it, and then you get this. And that's where that square root 3 comes from. And that's a critical measure because we use these ratios like this where the hypotenuse is 2, one side is 1, and then the other side is square root 3 with a 30 and a 60 degree angle. And if you have this triangle handy, of course, you can come up with these exact value ratios. So actually let me put this in here. Exact value ratios for 30 degrees, 45 degrees, and 60 degrees. So the sine of 30 is 1/2. Now that's no problem because of course your calculator will tell you that. If you press sine 30 in degree mode, you'll get 0.5. But the issue is on the cosine of 30 because the cos of 30, side adjacent over hypotenuse, is square root 3 over 2. The square root 3 over 2 is not, you cannot get that on your calculator. So what you need to do is remember, you have to have these ones down because your calculator is going to give you 0.8660. But you have to know that one. Now I'm going to summarize the methods that people commonly use to memorize them, but basically it's making the effort to get them down. Some people will draw these little triangles, such as you see in front of you, and they'll refer to that throughout an exam or an exercise. Other people will refer to the unit circle, which will be coming at the end of the lesson. Other people will, and this is what I did when I was a young person taking this, I would key cosine 30 into my calculator, and I would get the decimal value of 0.8660. And then I remembered, well, 0.8660 is square root 3 over 2. And of course, it's easy to verify. If you forgot that, you just drive it root 3 divided by 2, and you get that. So I tended to make the memorization based on the calculated, the decimal, and the root 3 over 2. It worked very well. But you have to find what works for you is essentially it. But you need to have it, and you need to be accurate, and you need to be fairly quick. Tan of 30 is 1 over root 3. You don't work with this one too much. That's about 0.58. And they're all obtainable from this diagram. And then the 60 degree ones, sine of 60 is root 3 over 2, of course. Then the cosine of 60 is 1 over 2, so adjacent over hypotenuse. And then the tan of 60 is square root 3. Now that's about 1.7 if you decimalized it. You don't work with the tan ones as much, but they do show up. And there you go. Then the next batch of same thing actually, but in radian measure, which is how you're going to see it mostly. So pi over 6, you can check this through conversion, or you might remember it is 30 degrees. Pi over 3 is 60 degrees. Very important equivalents that you work with a lot. So I wouldn't expect you to be using that conversion formula for 60 degrees and for 30 degrees very often. You should have those ones down. And everything is the same. So there's the 30 degree ones. The sine of pi over 6 is 1/2. So if you were in rad mode on your calculator, you would go sine and then pi divided by 6, and you would get 0.5. So if you're in rad mode, you can get these ones, and they'll give you the same value that you would have gotten had you entered a degree measure in and had your calculator in degree mode. And then here's the other ones for 60 degrees. The sine of pi over 6 is root 3 over 2. So the ratio is root 3 over 2. The angle is pi over 3. And when you take the sine of pi over 3, all you're doing really is, in its simplest exact form, you're finding out what the ratio of the opposite side to the hypotenuse is. And there we go. Now let's try a few requiring these and then move on to the 45 degree ones. So the sine of 5 pi over 6 and how we go about evaluating this one. Now there's a couple ways, there's more than a couple ways. There's a couple ways that I'm going to show you. First off, the really long conservative method, which your brain will be doing if you solve it, but probably faster. If you really want to invest the time in, and if you're new to this business, what you do is you convert to degrees. Now I don't recommend this, and I'm going to do it for the first few just to get a practice the conversions, but it's a way to make it work. So you would go the sine of 150 degrees, which is what 5 pi over 6 is. And then you would recognize that a 150 degree angle is in quadrant 2, because you take it from there. And that gives you a reference angle of 30 degrees. Now your reference angle is the angle you're concerned with, because really this is the sine of 30 degrees. 150 degrees is telling you that. It's telling you that it's a 30 degree angle in quadrant 2. And that will tell you the sine. And sine, the sine ratio, is positive in quadrant 2. So you take a look at what we've established, the chart, and you'll get 1/2. Positive 1/2 because sine is positive there. Now had you keyed this into your calculator, you would have got the sine of 5 pi divided by 6, enter, and then you get 1/2. Now the next one, cosine squared of 11 pi over 6. Now when you have exponents, as you know, for trig ratios, it really is all being squared. So the exponent goes outside. You take the cosine of that ratio and then square it. Now the long method, and this just goes to show you how much energy you can invest in this, and it's like a 1-mark question or less really. 11 pi over 6, if you convert it into degrees, is 330 degrees, and then you square the whole thing. Now the cosine of 330 degrees, right there, so that's a 30 degree reference angle. So what we really want is the cosine of 30 degrees in quadrant 4. Now cosine is positive in quadrant 4. So we end up getting root 3 over 2, which is the cosine of 30 degrees, and then positive. Now when we square that, root 3 over 2 all squared, we will then get 3 over 4. And that's our answer. Now, had you used your calculator, this is what would have happened. You would have got the cosine, if you're in rads, of 11 pi divided by 6, make sure you're in radian mode, and then squared. And then you'll get 0.75. So the thing is, even though those radicals are a problem, they're not a problem when you square things, because that turns into the radical will go away. Try a few more. Now cosecant, I haven't directly looked at the reciprocal ratios yet, but cosecant theta of any angle theta is equal to 1 over sine. It's the reciprocal of the sine ratio. So this is equal to 1 over the sine of 7 pi over 6. Now that would then take us to 1 over the sine of, well, 7 pi over 6, you can check it out, is 210 degrees. And 210 degrees, we're getting a lot of these 30-degree reference angles, but that's what it would be in quadrant 3. So really what we want is the sine of 30 degrees in quadrant 3. So I'm doing about as much work as you can for these questions. You do want to be much quicker processing this in your head. Sine of 30 we've already established is 1/2. Because it's in quadrant 3, it's negative. So this one is actually equal to 1 over negative 1/2. So if you divide this out, that's the reciprocal of negative 1 over 2. So it's negative 2. There as well, if you use your calculator, you get the answer very quickly. You would go 1 divided by the sine of 7 pi over 6. And then that would be your answer, negative 2. Now the thing of it is, that calculator method is fine, except that when you have a radical like root 3 over 2, then it will not work it out exactly. It will be decimalized. So you have to be ready to either know what that means or else just avoid those ones. What most people do, I think, is use their calculator quite a bit, except for the simple ones that they don't need to. And then if they have to adjust and think, then they do so. Next question is the secant squared of pi. So I'm throwing in a few variations of things that don't fit into those exact ones that we've seen. See, really, this is the secant of 180 degrees all squared. And that is equal to 1 over the cosine of 180 degrees squared. Now, the cosine of 180 is an interesting question because that's what we call a quadranto. It's on one of the corners. And the cos of 180, if you use your calculator, will be negative 1. And when we go to the unit circle, a lot of those ones that you maybe have forgotten, we'll have a chance to review. But this is what we get. So 1 divided by negative 1 squared is just equal to 1. Try it on your calculator if you're not sure. Go 1 divided by the cosine of pi squared. Then the tan of 135. I snuck this one in because tan of 135 is not a special angle we've looked at yet. Most of you will be familiar with it from earlier studies. So I'm just going to use my calculator in degree mode and see where it goes. And if you do that, and make sure you're in degrees, you will get negative 1. The reason for that is that 135 degrees is a 45-degree reference angle in quadrant 2. So really what we're doing is taking the tan of 45 in quadrant 2. Tan of 45 is always equal to 1, but because you're in quadrant 2, it'll be negative 1. Now there is a review lesson on the cast rule and the signs of the trig functions. It is uploaded, so if you need to review that, please have a look at it. Now, speaking of this 45-degree angle, let's take a look at a triangle, an isosceles triangle with two 45-degree angles in it like this. So the three sides would be, two equal sides are 1 and 1, and then the hypotenuse is square root 2. And then it means the sine of 45 is 1 over root 2. Now that's an acceptable form, but you can also write it in rationalized form, which is the way a lot of people are familiar with it from 30 pure. You don't have to. There's really no advantage to rationalizing these ones except being able to do it, because it's it might lead to a simplification. But in terms of right or wrong, it's not all that important. And then cos of 45 is 1 over root 2, or same thing, root 2 over 2. So the advantage of 45 degrees is that these are the sine and the cosine ratios are the same. And if you decimalized it, this is what you'd get, 0.7071. And again, that's how I did it when I was taking these. The instructor tried to, get us to memorize them, and in a sense I did, but I figured out quickly, well, go sine 45 on your calculator, and that's 0.7071. That is equal to 1 over root 2. So I didn't have any problem with it. So it's one of many ways to deal with them. And then the big one, or the easy one, is that tan 45 is equal to 1. So that's good. And the same thing would be true in rads, which is where we spend most of our time, except that 45 degrees in rads is pi over 4. And then the ratios would look like this. So on your calculator, if you're in rad mode, and you always have to be aware of what mode you're in, you'll probably be in rads most of the time, but still, you need to be aware of it. There's times when you do want to be in degrees for solving some problems. So I won't linger over this one long. Let's get right down to some evaluate questions, and there's a few interesting things happening with these. The tan of 5 pi over 4 squared, if it's squared, we know our calculator will handle it anyways. But this really is the tan of 225 degrees, so I'm cheating in this one, just for a little bit longer, all squared. So that is, in fact, a 45-degree reference angle in quadrant 3. So what we really want is the tan of 45 in quadrant 3. So the tan of 45 is equal to 1. Because you're in quadrant 3, tan is positive, so it will be positive 1. And then when we square it, well, 1 squared is just equal to 1. Your calculator will tell you that if you went through it like that. Next question, the sine of 7 pi over 4. Well, the sine of 7 pi over 4 is going to be equal to, if you converted 7 pi over 4 into degrees, you'd get 315 degrees. And 315 degrees is a 45-degree reference angle in quadrant 4. So this is sine of 45 in quadrant 4. Sine of 45 is 1 over root 2. Because it's in quadrant 4, it's negative 1 over root 2. Or negative root 2 over 2, however you wanted to write it. So sine is negative in quadrants 3 and 4. So anything on the bottom below the x-axis, sine would be negative. Calculator would help you with that, but it would give you the decimal version of it. Now the secant of negative 225, because it is a reciprocal ratio, this is 1 over the cos of negative 225. So keep in mind that as the reciprocals go, they're always starting with a different letter. Secant is not the reciprocal of sine, which starts with S. It's the reciprocal of cos, which starts with C. And then the cosine of negative 225 would be taking you around this way. So in fact, it's the cosine of 45 degrees in quadrant 2. And the cosine of 45 is equal to root 2 over 2, or 1 over root 2. And because you're in quadrant 2, it is negative. So we also get negative root 2 over 2. Try it on your calculator, and you will get negative 0.7071. Cosine is negative in quadrant 2 and quadrant 3. And then number 4 is an interesting one. I threw this one in, even though it's again a quadrantal. And this one might mess you up a little bit, because it's one of the few that you cannot use your calculator on at all. 3 pi over 2 is 270 degrees. And cotangent is the reciprocal of tan. So this is 1 over the tan of 270. The problem is, if you take a look at this quadrantal, 270 is right there. And the tan of 270 is undefined. That's a problem. But that doesn't mean that cotangent is undefined. So when you take the reciprocal of this, you in fact will be getting 0 for it. It works out. Now your calculator won't give you that. If you went 1 divided by tan 270, it shuts you down because you can't take the tangent ratio for 270 degrees. But the way it works with these is that tan theta, in terms of x, y, and r, is equal to y over x. So cotangent is equal to x over y. And then what happens is that because the x value is 0, then it's okay, because it'll be 0 over some number. Now that may seem a little confusing, although again I think everybody has covered this before. On the unit circle, which is coming right up, we get a chance to take a look at everything. The unit circle basically holds the keys to the universe, the trig universe. It's all there, or there's a way to find everything. The unit circle is a circle centered at origin with r is equal to 1. The equation is x squared plus y squared is equal to 1. And the good thing about the unit circle, the many good things, but the one thing first off, here is your circle. I've got some of the angles drawn. Is that and I'll write this down in a second, is that the coordinates of the points on the unit circle are always going to give you the cosine and the sine ratio. So this point there, for example, the x coordinate is the cosine of theta. The y coordinate is the sine of theta. So the unit circle, if you put in all the coordinates, gives you the cos and sine ratios for all the main angles. And the reason for that is cos theta in general is equal to x over r. So because r is equal to 1, then the cosine of theta is equal to x over 1. And the same thing is true for sine. Sine theta in general is defined on the coordinate plane as y over r. So sine theta is equal to y over 1. So sine theta is equal to 1. Oh, or is equal to y, excuse me. So if we take a look at this, I'm drawing in first off the corners. And that's what tells us that if you're dealing with a 0-degree angle, the cosine of 0 degrees, or 0 rads, is equal to 1. Check it on your calculator. It'll tell you that. And the sine of 0 degrees, or 0 rads, is equal to 0. So the unit circle is very helpful for four quadrantals. Most people memorize them anyways, but if you needed to take the cosine of 270 degrees, it's going to be equal to 0. Just like the sine of 270 degrees is equal to -1. And so that means the domain and range are from -1 to +1 for both cos and sine. And this also helps with the quadrantals, because tan of pi, for example, would be equal to y over x. So the tan of pi would be equal to the y value. Pi is 180 degrees, so 0 over -1. And so therefore the tan of pi rads is equal to 0. Now your calculator will tell you that, so it's not a problem. In fact, the calculator tells you all the quadrantals except for the cosecants and the secants. The reciprocal ones, it does not, because if it's undefined, your calculator cannot take the reciprocal of an undefined value. So there is a little bit of knowledge that's required for these. Now I put those quadrantals in rads, so I wrote 0 rads as 2 pi, pi over 2, pi, and 3 pi over 2. And then if you looked at quadrant 1, there's your 30-degree angle, pi over 6. There's your 45-degree angle, pi over 4. There's your 60-degree angle, pi over 3. And if you were to get your quadrant 1 measurements down, the ratios down, this is giving you the sine and the cos ratios. So this means that the cosine of pi over 6 is equal to root 3 over 2. That's a true story. And then the sine of pi over 6 is equal to 1/2. We know that as well, but it's all here on the unit circle. Contains all the information. So the cos of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. And then the cosine of 60 degrees, or pi over 3, is 1/2. The sine of pi over 3 is root 3 over 2. So in quadrant 1, everything is positive. So the next slide is going to show this around the entire circle. So there's quadrant 1. In quadrant 2, these are the angle measurements for those reference angles. So notice that a 30-degree angle, pi over 6, is still going to have a pi as 6 as a denominator. So you know that this is a multiple of pi over 6. So by getting familiar with a circle, you don't need to use those conversion formulas. 3 pi over 4 is a 45-degree reference angle. 2 pi over 3 is a 60-degree reference angle because it's a multiple of pi over 3. And then the ratios that would go, oh, let me finish these off first. Quadrant 3, same thing. 7 pi over 6 is the 30-degree reference angle. 5 pi over 4 is the 45-degree reference angle. 4 pi over 3 is the 60-degree reference angle. And then in quadrant 4, 5 pi over 3 is the 60. 7 pi over 4 is the 45. 11 pi over 6 is the 30-degree reference angle. So you know quadrant 1, you can very quickly do the calculation to get the other ones in the other quadrants. And then the ratios, if you're in quadrant 2, notice how the cosine ratio, the cosine of 2 pi over 3, it's 1/2, just as it is in quadrant 1, but it's negative because x is negative in quadrant 2. So cosine is negative in quadrant 2. So that's true for all these ratios. Same numbers, but cos is negative, sine is positive. And then when you get to quadrant 3, both x and y, both cos and sine are negative, but notice the values are the same. 7 pi over 6 has got the same ratios as 5 pi over 6, just both negative. 5 pi over 4, the same as. 4 pi over 3, they're both negative. So the tan and the cotangent would be positive in quadrant 3 because a negative divided by a negative will give you a positive. And then so on. Quadrant 4, the cosine is positive, sine is negative for each of these three ratios. So the unit circle gives you the means to work out every exact value for the special angles, 30, 45, 60, and also the radian measure equivalents, and very importantly, the quadrantals, so the corner ones, so that you can get those down without a lot of fuss. So you want to keep a unit circle handy for a lot of the questions you do. Can't take it in with you on exams, but it's a good way to memorize everything. So I'm going to stop right there, but thank you for your time.